Hello, everybody. This is Mr. Strager, and welcome back to another Big Ideas lesson. Today, we are going to be talking about lesson 6.3. And before we get too deep into things, this lesson is going to be a little bit different. You may need to have access to the Desmos graph that you're going to be seeing in the video in a little bit. This can be found on our Canvas page at the very bottom of the page in Unit 6, Desmos for 6.3. If you don't have access to this Desmos, just feel free to email me and I'll be more than happy to share it with you. That said, let's get started. So today we're talking about exponential functions. And we've talked about different types of functions in the past, specifically linear functions. And linear functions were equations that we could use to make a straight line. Hopefully we remember that the equation of a linear function is y equals mx plus b, or f of x equals mx plus b. Exponential functions are another type of function that we talk about in Algebra 1. There's a total of 3 of them that we're going to talk about through the year. The last one's going to be a little bit of a secret until later. Exponential functions, I would say, are a little bit easier than linear functions, at least in terms of how to work with them mathematically and how to find them. Exponential functions are just made up of 3 small pieces. Well, 4 if you count the y. It's y equals a times b to the x. So we just have a, then b being taken to the x power. Now, when we look at this, it seems very different from a linear function, and that's for a good reason. This is going to produce a much stranger looking graph than just a straight line. However, we're going to be able to work with it and see what we get. So what I want to do now is on my screen, I'm going to put up the Desmos activity. On the Desmos activity, you may notice a couple of things. It has, of course, our y equals ab to the x right over here on the left-hand side. You'll also notice that we have 2 sliders. By adjusting these sliders, you'll be able to actually change the values in the function. So what this is saying is y equals, since a is 1, it would be 1. Since b is 1, it would be 1 here. And that's being raised to the x power. And if I very briefly change the color of this one here, oops, you'll actually see, I apologize, you'll actually see that it will match up entirely with the one that we have right now. Bam, there's our green one, and there's our original. So all we're doing is we're plugging in different values of a and b. However, if I change a to 2, my red line moves, or to 3, or to 4, or 5. In fact, I'm moving my red line around just by changing the a value. What does the a value change though? And how does this impact us? For this, we're going to need to take a brief look back at our notes. At the very bottom of your notes page, where it says notes, I want you to do the following. I want you to split your page up like so. 4 boxes and 2 labels up top. On this first label, we're going to say a is the blank. And we're going to figure out what a represents on an exponential function. We're also going to do b is the blank. And we're going to talk about that. In each of the boxes, I want you to copy down the following. And it's very important that you get this exactly as it is written. In the top left box, we're going to see what happens when a is bigger than 0 and b is bigger than 1. In the top right box, we're still going to see what happens when a is bigger than 0, but this time b is going to be in between 0 and 1. In the bottom left, we're going to see what happens when a is less than 0 and b is more than 1. And in the bottom right box, we're going to see what happens when a is less than 0 and b is in between 0 and 1. This won't mean very much for now, but what we're going to do is this. We're going to start off by analyzing one box at a time in Desmos. We're going to see what happens exactly when we say our a value can be anything as long as it's bigger than 0, and our b value can be anything as long as it's bigger than 1. We're going to try to see what the graph looks like, where on the grid our graph is, as well as what direction it's going. Sound like a plan? Let's head back to Desmos. In Desmos, you'll see that this graph is actually set up in a way where our a values go down to 0 and above, and our b values go from 1 and above. If you ever wanted to change this, let's say we want to figure out what happens when a is less than 0, we just have to change the inequality. Let's say it goes from -5 to a maximum of 0. Now it's below the x-axis. You may have already picked up on what the a value represents here. The a value, if I press play and just let it play through, seems to change how high up or low down the graph is, right? But it's even more than that. Let's see what happens when we change our b. As of right now, this is just a straight line. However, when my b value is different than 1, watch what happens. It begins to curve. The lower the number, the more shallow the curve. The higher the number, the more steep the curve. We see some interesting things here. On the left-hand side, our graph starts getting closer to 0. You see how it gets closer to the x-axis on the left? The further we go, it almost presses up against the x-axis. Meanwhile, on the right-hand side, the most dramatic change, it starts sloping up, and it goes up and up and up and up and up, and it's turning into a straight line, but it never quite gets there. Well, let's see what happens when we change our a value now. Okay, the whole graph isn't moving up and down anymore, just parts of it are. Specifically, what part do we notice moving up and down? Well, if I pause here at a equals 2, for instance, what equals 2? What is at 2? In fact, if I draw a big line through 2, we might be able to see something. So if I draw a line going horizontally through y equals 2, what do we notice? It turns out our y-intercept is at 2. That is what the a does. Our value of a actually tells us what our y-intercept is. If I change it to 3, take a look where y-intercept is. It's at 0, 3. Or if I change it to 1, it's all the way down here at 1. In other words, all a tells us is what the y-intercept is. If our a is positive, our y-intercept has to also be positive. So our graph is above the x-axis. You can see this as we animate both values. As we animate both values, our line changes both in its curvature as well as what the a value is. So we're going to try moving on to something a little bit different now. We're going to try to see exactly what happens when we change these values up. Before we do, I want us to jump back to the notes just for a quick second. If we go back to our notes page, in the first box, you'll see that we've talked about this exact situation. Our a value was positive, our b value is bigger than 1. Well, we noticed a couple of things. Our graph was located above the x-axis, for one thing. It was always positive. It never dipped below the x-axis. We can draw a little bit of a sketch of it as well. It sort of looks like this. leveling out to the left, and going up and to the right. So that's how we can describe the direction. It goes up and to the right. There is a name for this specific orientation. When your graph is above the x-axis, so our a is positive, and our graph seems to keep growing up and up and up and to the right, we call this positive growth. We can also fill in this blank up here. A is our y-intercept. So whatever number is there for A, that's going to be where our graph starts on the y-axis. Here's what I'd like you to do. In our Desmos activity, I want you to change up the values a little bit and see what you get. Again, this activity can be found in our Canvas page. I'm also going to put it in the description of this YouTube video, so you'll be able to access it. Let's take a look at this right box, and I'll just show you how to adjust the values. Let's say we go back to Desmos, and you'll notice that over here, we want to see what happens when A is bigger than 0, but B is in between 0 and 1. Well, if we go back to Desmos, we'll see that our A is bigger than 0, our B is not in between 0 and 1. To change it, click on the number, and then down below where you see the inequality, change it to be what you want. So now B is between 0 and 1, A is equal to 1. I'm going to pause the recording here, and I want you to do the same because I want you to try this out for yourself. Ask yourself the same 3 questions. Where is the graph? Above the x-axis, below, to the left, to the right? Where is it? What direction does our graph go in? And what will our graph look like? Pause the video here. I'm going to pause as well. And in a second, I'll show you what each of these graphs looks like, and we'll talk about them. All right, everyone. This should be what we found for our first graph. You may notice that it always starts off as being flat when your A value is either 0 or 1, and your B value is 1 or 0. Change your B value and your A value a little bit until you get a curve, because exponentials are always curves. So let's talk about this one. This one is still always above the x-axis. It never goes above that middle line there. We can see that. So we would say this one is above the x-axis as well. As for the direction it goes, well, you can see it sort of curves up and to the left. So we would say that this graph goes up and to the left. And of course, you should sketch this one out. We'll talk about what this one is called in a little bit, but keep going. Try a different one. Try changing your A value to negative and your B value to be above 1. Pause the video here and let's see the next one. Hopefully you've had a chance to pause the video and try this one out for yourself as well. This one looks like this. A little bit different now. Where on the graph is it? Well, this one is not above the x-axis, it's entirely below it. No matter what I change my A value to be or my B value to be, the graph always sticks below the x-axis. What direction does it go in? Well, it seems to be flat on the left and then slowly go further down and to the right. So we could say this one goes down and to the right. And of course, you should sketch this graph as well. There's one more to try out for yourself. And it is important that you're able to try these out and experiment. Try the last one out. And we'll come together and talk about it in just a moment. For the last one, we should have gotten something that looks like this. Where is it? Well, it's below the x-axis again. What direction does it go? Well, this one is down and to the left. It goes down, further to the left it goes. And of course, we should also sketch this. Let's go back to our notes and just take a look at everything we have so far. All right, These are our findings so far. Our second graph was above the x-axis. It went up and to the left and looked like this. Because it's above the x-axis, we are also going to call this positive. However, we're going to use a different word than growth. Growth means as it goes from left to right, it goes up. It kind of gets further away from zero, I should say. If it goes closer to zero as we get from left to right, it's getting smaller and smaller and smaller and smaller, never quite making it to zero or below, but it keeps getting very, very close to zero. We call this decay. Kind of a grotesque word for it, but this is called positive decay. Well, what about over here? This is no longer above the x-axis, it's below. We call this one negative. And since it's getting further and further away from our x-axis, from zero, as it goes to the right, we also call this one growth. It's growing just in a negative direction. Last but not least, this one is also negative because it's below the x-axis, but we call this one decay. As it goes from left to right, it gets closer to zero, closer to our x-axis. So here we have it, positive growth, positive decay, negative growth, and negative decay. You may have noticed a couple of things. When A is bigger than zero, we call our graph positive. It's above the x-axis. When A is less than zero, we call it negative, below the x-axis. So our A value controls whether our graph is positive or negative because it's our y-intercept. What happens when B is greater than 1? Well, B is greater than 1 here and here, and we call them growth. When B is bigger than 1, our graph exhibits growth. And when B is in between 0 and 1, it exhibits decay. There's a name for how much a graph grows or decays by. We call this the growth factor. If you have a high growth factor, it means that you are growing very quickly or getting very, very negative very quickly. If you have a small growth factor, it means you are decaying, slowly, slowly, slowly pushing yourself towards zero. So this is what we have so far. We should also be able to predict what a graph will look like just based on these numbers. Let me give you an example of this, and I want you to try this out for yourself. Let's say I gave you the following equation. Y equals 3 times 5 to the x power. Okay, first things first, which letter is our, or which number I should say is our A and which one is our B? A is the number that doesn't have an exponent on it, and B is the one that does. If our A value is 3, what does that tell us? Well, if our A value is bigger than 0, it tells us that our graph is going to be positive. What about our B value? Our B value of 5? Well, we check and we see that a B value of 5 is not in between 0 and 1. It's bigger than 1. 5 is bigger than 1. This means we have a graph that will show positive growth. That means without even having to graph it, we know it's going to look something like this. Don't believe me? Let's go back to Desmos and try it out. Here is our previous graph. I'm just going to remove that one real quick. And I want to see what happens when I plug in y equals 3 times 5 to the x power. And lo and behold, what do we have? We have our graph. It looks exactly like we predicted. It has positive growth. Just from this equation, can you tell what the y-intercept is? Of course, you can tell it from the graph too, but the equation, our a value is 3. So our y-intercept is at 0, 3. This is huge. This is hugely fascinating because we can guess what a graph will look like without even having to graph it. But let's discuss how we actually would go about graphing this manually. Let's turn to page 181 in our notes. At the very bottom of page 181, we have the opportunity to actually graph something. Here on number 8, it gives us f of x equals -2 raised to the x power. Remember that f of x just means y. So this is really saying y equals -2 to the x power. Before we get started, I want to ask, what do you think our value of a is if we have this negative, then 2 to the x power? Well, since the number -2 is not being taken as our b value, and we'll learn that we will never have a negative b value, 2 is our b value, negative is kind of our a value. In other words, we really have -1 times 2 to the x. This is our graph of exponential growth. We have -1 times 2 to the x power. So already right off the bat, we know our a value is negative. That means we're going to end up with a negative graph. Our b value is bigger than 1. So it's going to be negative growth. We already know what our graph is going to look like. But we don't know exactly what it's going to look like. We don't know exactly where each of the points are. Whenever you don't know what a graph is going to look exactly like, the best way to figure it out is by use of a table. So we're going to set up a little bit of a table here. X is on top, y is on bottom, and we're going to split it up a little bit. I'm going to put, maybe that'll be enough values. I like to write -3 all the way going up to 3, and we're going to figure out what all of our y values are. This is very difficult to do. Before we jump into this, I think it might be very useful to take a look at problem number 5. Problem number 5 tells us that y equals 3 to the x power and x equals 5. Sort of like the situation we've got going on down here. We know what our x values are going to be because we just decided on a couple of them. Here, they're telling us what our x value is. So what do we do? Whenever we're asked to evaluate and they give us a value for x, we're meant to plug it in where x is. So for instance, this problem will become y equals 3 to the 5th power. And if you plug this in your calculator, 3 times 3 times 3 times 3 times 3 ends up giving us 243. Well, we can do something very similar down here. We know what our x values are. We just need to keep plugging them in. Let's start off simple. Let's start off with plugging in x equals 0. If we have y equals -2 to the 0 power, let's ask ourselves, what's being taken to the 0 power? Just the 2, right? If this was in parentheses, -2 would be taken to the 0 power, but just the 2 is being taken to the 0. Well, what's 2 to the 0 power? Anything to the 0 power is 1. So this is -1. Let's plug it into our table. 0, -1. Let's do this again with our next couple of numbers, with the positive numbers. If x equals 1, what we're really doing is y equals -2 to the 1st power. Well, we find what 2 to the 1st power is and then take the negative version of that. What is 2 to the 1st? 2 to the 1st power is just 2. So this is -2. Let's put that in our table. I want you to try plugging in x equals 2 and x equals 3 and see what you get. Pause the video here and see what you get. Hopefully you've had a chance to try this out. When you plug in 2 for x, you get -4, because this is really saying y equals -2 squared. 2 squared is 4. We put the negative in front, it's negative 4. 3 will give you negative 8. You may have noticed a little bit of a pattern, and this is going to be very helpful for figuring out how to fill in tables. Once you have 3 or 4 numbers, not 2, but 3 or 4, you can figure out what the pattern is of an exponential. In this case, what's happening as the numbers go up? Well, to get from -1 to -2, we multiply by 2. To get from -2 to -4, we multiply by 2. -4 to -8, we multiply by 2. The rule seems to be, as we multiply by 2's, we keep going up. If we go down then, we would have to do the opposite. What's the opposite of multiplying by 2? Dividing by 2. Instead of plugging in 2 to the negative first power, we can instead just follow the pattern going the opposite direction. 1/2 of -1 is -1/2. 1/2 of -1/2 is -1/4. 1/2 of -1/4 is -1/8. So we have a really good list of values here. But this is going to be tricky to graph. What I want you to do now is I want you to split this down the middle, but I want you to put your x-axis kind of near the top, because think about it. All our numbers are negative. It wouldn't make sense to graph above the x-axis. So let's give ourselves as much negative space as possible. Your goal when you graph an exponential is to put as many points down as you possibly can. So to graph 0, -1, it's going to be our y-intercept, -1 on the y-axis. 1, -2 is right here. 2, -4 is right here. 3, -8 is right here. And you start to see that we don't end up with a straight line, we end up with a curve. It's not the same as a linear equation. Just by seeing these 2 points, we wouldn't be able to accurately decide which way our graph is going to go. Because it could go, for all we know, straight down after this. It could go and be a very broad curve, go all the way over here. Until you graph as many points as possible, you don't know what your exponential will look like. To graph the fractions, you just need to estimate. So -1/2 is about right there. -1/4 is about right there. 1/8 is about right there. And we now have enough to sort of see what our graph will look like. As you connect your points, there are 2 rules to follow. Your exponential should never touch the x-axis. Just go alongside it. Something like this. As you follow the curve, your exponential should never go straight down, but it should get pretty dang close to being straight down. This is how we graph f of x equals -2 to the x power. There are 2 more quick problems I want us to go through. First problem is this. Deciding whether something is a linear or an exponential function. This is more review than anything, but the rule is this. We try to find the pattern as we look at the x's and a pattern as we go with the y's. And we decided that if our y's are increasing by adding or subtracting, this would be a linear function. But is this really linear? Not really. Here I would -4, here I would -2, I'd -1 to get to here. It seems like the rule is not going to be adding or subtracting something in our y's. Sure, the x's just keep adding 1's, but it seems like the rule is a little different for our y's. In fact, how do we get from 8 to 4 to 2 to 1? What's our rule? The rule here is that we are dividing by 2 each time. Think about it. 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. This is not linear. If your rule is that you multiply or divide by something every time, we call it an exponential. So a table is exponential if you multiply or divide by something every time. Keep in mind, we don't care about the x's. The x's we can keep just adding 1. The y's are what determine whether it's exponential or linear. So let's look at number 2. Are we adding or subtracting something every time, or are we multiplying or dividing? Well, to get from 3 to 7, we're really adding 4 here. Let's see if the pattern continues. 7 to 11 is adding 4, 11 to 15 is adding 4. So this would be linear, since we're adding or subtracting something every time. We say that this has a constant rate of change since we're adding or subtracting the same amount each time. We would say that this one does not have a constant rate of change because the amount of numbers it's changing by is changing every time. Here it changes by 4, here it changes by 2, here it changes by 1. The last problem type we're going to see is on page 182. You'll be given a graph or a table and be expected to make a function out of it. This is tough, but we have to remember what A and B are. Whatever our y-intercept is, that'll be what we put for our letter A. And however much we're growing or shrinking by every time is what we'll put for B. So let's try number 12. Let's look at this table. We know we're going to want to put our answer in the form y equals AB to the x. What is our y-intercept here? Well, our y-intercept is whatever our y value is when x is 0. In this case, when x is 0, f of x is 3. So we know our value of A is 3. This equation is y equals 3 times something to the x. But what is that something? To find our growth factor, we just have to figure out how much we're multiplying or dividing by every time. And in the table, it's particularly easy. To get from 3 to 18 to 108 to 648, we are multiplying by 6 each time. So our growth factor is 6. Our equation is y equals 3 times 6 to the x power. Thank you so much, everybody. I know these notes were a little bit weirder and a little bit longer, but hopefully we were able to learn something from them. That said, that is the end of the notes for today. Have a fantastic rest of your day.